Thank you. Welcome, everyone. A little bit of introduction to what I do and the company I'm working at. I'm a performance analyst at IMC, which is a trading company, a technology-driven trading company. It offices at Amsterdam, Chicago, and Sydney. And we value automation a lot, and our networks are a core part of our business. As in, like, if Donald Trump makes a tweet, we would rather know it within a couple of seconds so that we could brace for impact and not lose a lot of money out of it. So my role as a performance analyst, it's the performance of the systems and networks and not the people. And my background is in computer engineering. And yeah, finally, we are hiring. So if you are interested in moving to one of these cities, Amsterdam, Chicago, or Sydney, feel free to check out the website. So I'll talk about this problem of quantifying hidden variables as a pragmatist outsider, like not a statistician or an expert in Bayesian inference. I just want to get things done with little work with fewer lines of code as possible. So, and I will keep this at a very high level since, yeah, this is a short presentation and right before lunch, and I'm getting quite hungry. And there will be just a high level overview of the problem, 3 lines of Python code, and a little bit of stuff with math here and there. And the main takeaway from this, if you forget everything else, is that for this specific kind of problem of hidden variables, if you can formulate your problem in terms of random variables, you can use this type of technique to tackle it. So I'll start with the problem. We have this data. As usual, columns are features, rows correspond to observations. And what we want to really find is some variable that is not actually presented in these columns. So that could be because it's just impossible to know. It could be that we can estimate it later, but it takes time. Or it could be because it's expensive to estimate, so that once in a while you will get this value, but it's not, you cannot use it as a part of your model building. So I'm giving here a more concrete example of poker. Unfortunately, the actual example I'm going to work on won't be as entertaining as poker. But if we think of poker hands, it could be like each poker hand could be considered an observation, and each action by each participant could be represented as a column. And the hidden variable you are trying to guess is when someone is bluffing, or maybe at a higher level there, how often do they bluff at a certain situation. So quantifying hidden variables, like if the variable is completely out of reach, then this doesn't really make sense. So what we actually do is we have data, we have knowledge, and we want to bridge the gap with our model. So that's why I mentioned probability distributions. They help bridging the gap between your data and what you know about the underlying system. So the actual scenario we have here is we have this communication over some unreliable channel. We just want to get data from endpoint 1 to endpoint 2. But we lack control on some parts of the network. For instance, it could be managed by a third party. And we know that at this part that we don't have control over, our messages, like the packets, can get dropped. And when that happens, in between these two nodes in the hidden part, they get retransmitted until success. And we don't know when a packet gets dropped. We only know the latency from point A to point B. So in this problem, what we are looking at is the hidden variables we care about are either like number of drops at a given message, or the probability of dropping. In our case, actually, the probability matters more because we use it to quantify the quality of the medium. And the data we know is for maybe 10,000 messages. We know how much it took from endpoint A to endpoint B. And we also know, have expert knowledge on how much time it should take between these hops in the network. So, we don't know individual cases, but we know how the system should behave. We know the underlying distributions behind it. So, this is how the data looks like in this problem, which is synthetic data. You can see that, it's most likely a mixture of distributions, but that's part of the model to take care of. So I will move on. So, and our knowledge is, we know the distribution of each and every hop. We know that there will be one or more attempts. We know that there's a fixed probability of packets getting dropped. We know that we can just formulate the one-way delay as a sum of these individual delays. And we have an idea about where the probability drops, the region that we should search for, between 10% to 40%. And we can say that since we have a fixed probability of dropping, the number of attempts it takes from node number 1 to node number 2, it's given by the geometric distribution. So this is a problem that you have different kinds of solutions that are possible. So some extremes are, you might want to, for instance, just go full simulationist, just code every part of the system, run a simulation 100,000 times with different parameters, and search among these parameters until you find something that explains your data the best. You could go all the other way and just go completely analytical as much as possible, and just try to solve these by hand, get a final distribution to maximum likelihood on the data. Or you could just present the data to your expert and have them eyeball it and just make educated guesses on what the probability of drop is. So each comes with their own trade-offs, and Bayesian inference, actually what it does is it provides a trade-off between completely simulationist versus the analytical approach. So what you do is you start with a hypothesis which are represented by some parameters, and you update your belief with evidence. So you would have a prior distribution of your parameter, which could be the probability of dropping, and then you have a final distribution after your model is presented with the evidence. So the advantage of this is you can still pretty much encode parts of your system, and you can treat everything you don't know as random variables. So that means not just stuff that happens on the fly, like coin flips, but also the stuff that you don't know as in probability of the coin being fair, for instance, or in our case, the probability of packet being dropped. So this allows you to first make an elegant formulation of the problem. It allows you to constrain the search space based on your beliefs. And it also allows you to take advantage of packages that are out there to numerically solve this problem. Because once the problem gets complex enough, there's actually analytical solution is not really possible anymore. So people always go for a numerical way. And I'll talk about the PyMC package in here. I haven't actually used the other alternatives. But yeah, just so you know all the options that are out there. And if you want to know a little bit more about the approximation methods, there are two main ones, Markov chain Monte Carlo and variational inference. you can take a look at the paper at the bottom of the slide. By the way, how many people have heard of PyMC already? Great. There are chances that you already know this more than I do, because I'm an outsider, as I said. So these are the 3 lines of code that I mentioned to formulate the problem. And like with PyMC, you can, so the slightly darker part is the observed variable, the one-way delay between point A to point B. Then you can sort of model this as a Gaussian mixture, and then these weights could have Dirichlet priors. And what you can also do is first determine what the probability of dropping, or inversely probability of success from these weights. What you can also do is you just draw new variables after fitting your data, and then sort of do a sanity check on your model. In our case, after running everything, we had the probability was centered around 0.79, which is the probability of success, not probability of dropping, because of the way geometric distribution is. And it was like there were 4 runs in there. We could say that the Markov chain Monte Carlo simulations, they arrive to a pretty stable state. Is that the actual probability of dropping? That's of course another question. To sum it up, this I presented you one way to bridge the gap between the knowledge and data. And there are some challenges with that. If you're not familiar with the domain, that like there can be some counter intuitive parts in the modeling, and debugging can be an issue. Like you might not know what you have done wrong to cause your model not to converge if it gets complex enough. And you have to formulate your problem in terms of probability distributions, so that that means your observed data should either, if there isn't an available distribution, you would have to formulate it yourself, or transform your data in a way so that it can be it can be referred as a existing distribution in the package. I presented the links in here to PyMC package, and once the conference is over, I will upload the actual code that I used for this problem and the datasets to the GitHub page in here. Thanks for listening. Questions? I actually played quite a bit with different priors, and the results really vary. For instance, I tried with a uniform prior versus a beta prior for probability of dropping. It seemed to converge faster when I had a beta prior. I also tried to formulate this problem in a million different ways. And in the end, actually the best, the fastest way I got was to, first forget about the probability of dropping at all, just do the Dirichlet prior. And then from there, you can, from the weights of the, Gaussian mixture it produces, you can actually infer, the probability of, dropping. And then you can verify that if these weights actually, follow a geometric distribution as a sanity check. Yeah.
I wonder how you came up with your probabilistic formulation. You just look at the data and then kind of guess the model, or did you talk with domain experts here?
A little bit of both. So what they do have is for the network equipment. Sorry, actually, let me repeat the question. How did I formulate the probability distributions? So there are two ways. First, the experts provide you some documentation. In our case, the main component of like the variance in the distribution comes from actually the processing by these nodes. And they tend to provide documents that say it follows this distribution. It's how it looks like. So you already have an idea. But we usually go a step further. If we, like, usually we have the money to just purchase the equipment, get it in a lab and try it out ourselves and fit a distribution to it. Yep. Yeah, actually, yeah, the question is, yeah, how much does this scale? Can we go with million parameters? In my experience, yeah, I haven't gone over more than actually a vector of size 20. Most of the time I was looking actually very specific points that I was trying to find, so I didn't try. From what I understand is with Markov chain Monte Carlo part, it doesn't scale very well. It's more like you have a well-formulated problem and you want to have your solution as close to exact as possible. Whereas with variational inference, it scales better to large data sizes, probably large parameters too, but I didn't check it myself. Yes? Yeah, so in trading, there are, sorry, actually question again. How much does this help with our trading, with the performance and networks? Did I get it right? Yeah. So in trading, there are two ways to make a profit. You either have to be smart or you have to be fast, or both, of course. And the trading strategies that rely more on being fast part, they actually need this. The other thing is that companies like mine, they are market makers, which means that so in an ideal market, when you want to trade something, there is always a counterparty, but in real world that's not always possible. So exchanges get market makers to do this. And market makers always quote for the products that are out there. But what you don't want is to have a quote out there and then Trump says something, but your quote is which massively drops or surges the price, and your quote is stale. And then you just lose a lot of money because you've been quoting on a price that is actually no longer valid. So in these kinds of situations, performance matters a lot, and it can, yeah, it does have a significant impact on daily profit. Okay, thank you very much.